Object-Oriented Classification tutorial. A tutorial on how to use open-source software, the ORFEO application in QGIS, and remotely sense data to perform object-oriented classifications. Instructions compiled by Miguel Pavón, working with the Bird Conservancy of the Rockies for the Desert Landscape Conservation Cooperative, DLCC. It's not every day that you say, I want to make an object-oriented classification today. Check land cover classes over time to evaluate and document where current land management practices are helping to conserve habitat and landscape. We need a plan, some ingredients and methods. Next, we are going to talk about ground truthing, how to develop training polygons and accuracy assessment polygons. Hello. Hi, my name is Miguel Pavón. I'm working with the Bird Conservancy of the Rockies for the DLCC and also the Desert Landscape Conservation Cooperative. On how to make an OOC, how to make an object-oriented classification work. It's not every day that you wake up in the morning and say, I want to make an object-oriented classification. And then you can go to the grocery store or you can go to the bank. There is some planning involved in it. You need to figure out what kind of remote sensing imagery you are going to use. You need to figure out the time of the year that you want, or if you want multiple times of the year. And also a very important thing is to get your ground control points, your reference training polygons, your ground truthing. Like for example, today we are at a grassland, and we are going to talk about how to collect ground reference polygons here in this grassland. So in the past, we needed a GPS unit and a notebook and camera to make that work. A GPS units come in different kinds of prices and ranges. This is one of the cheapest ones. The camera is also one of the cheapest ones that you can have. Also, some people now can use their smartphone. What we can do here is to take pictures, notes, and GPS coordinates. Like for example, we know that we have a set of latitude and longitude at this point. Let me show it to you. And we also know that we can use those coordinates on top of a concurrent Landsat image to develop a grassland polygon. We know that every pixel in Landsat is 30 meters by 30 meters. How big is 30 meters? Let me go as far as 30 meters, and one pixel will be approximately that distance times 30 meters wide. Let's do that. Note that at this latitude, 1 arc second is approximately 100 feet, 30 meters, or 1 Landsat pixel. This is 30 meters long. By 30 meters wide. There it is. I just walk around 1 Landsat pixel. There are several pixels of grassland. That should be visible in a concurrent Landsat scene. We take one picture from the top, nadir, and 4 oblique pictures in the 4 cardinal directions to give us an idea of how big is this extension of grassland. Looking east, looking south, looking west, and looking north. We can record our coordinates with the Compass app in our phone and capture it, and or also with our GPS unit. So we make sure we have our pictures from top down and 4 cardinal directions. Our next class to capture is water. Make sure that you have several reference polygons, 10 or more, per class that you want to map. Take pictures in the direction of the water. Water polygons may be tricky because we do not have a boat to capture a point. What you can do is to take some notes and take your GPS reading as close to the water as you can. So we have our water GPS location. Our next class to capture is bare earth. We take several locations and several photographs per location. This is our forest class. We capture several locations and several photos per location. Agricultural classes may have a mix of crops. Urban class will be a mix of concrete, asphalt, buildings, cars, and some green areas. Capture a variety of locations with several conditions. The last class for which we take coordinates to create reference polygons is brushland. It may be a mix of bushes with grasses. Repeat until you have a good number of samples, 10 or more per class. Practice will make you gain confidence with the number of samples needed per class. Remember that you need reference polygons for the training the classifier process and different ones for the accuracy assessment. Hello, this is a tutorial on how to download and install the QGIS and ORFEO Toolbox needed for an open source object-oriented classification. First, open your browser and navigate to www.qgis.org. Click on Download Now. There are several platforms from which to choose from. There is Windows, Mac OS X, Linux, etc. as options. You will pick the one depending on your platform. For this tutorial, we will choose Windows 64-bit. We pick the option for advanced users, OSGeo 4W, Network Installer, 64-bit. We click on this link to start the download that we need. We save the file that we need under downloads, and it takes a few seconds to a minute, depending on your internet connection. We go to Downloads in your browser to open the executable. For the setup, we click on the Advanced Install button, and then we click Next. We want to install it from the internet and install it for all the users. Optionally, create an icon on desktop. Click Next. Select a temporary local package directory and a name. We want to use a direct connection to QGIS website. This is the QGIS website from which the software and options will be downloaded. Click Next. We need to select which packages we need to install. Default will make a minimal installation. We click on the revolving arrows until we see All Install as our option. If you click on the plus signs, you can see all the different tools that you can install and their versions. As you can see, there are plenty. If space is not an issue, we can proceed with the installation all by clicking Next. The download of the packages starts, asking to agree to license agreements when needed. This may take several minutes. At the end, you click Finish. The software downloads and installation completes, and you will have QGIS and ORFEO Toolbox installed in your computer. After the installation, you will now have an icon on your desktop and the option to run the app from the Programs and Features menu in Windows. Different platforms may behave a little differently. In the case we have QGIS Desktop 2.18.7, we click on it and it will open the app for us. This is an example of a successful installation. Notice under Processing Toolbox we have ORFEO and the segmentation tools needed for the object-oriented classification. In this part of the tutorial, we want to talk about Earth Explorer. This is a tool to select and download an image to use in our object-oriented classification. First, we go to the Earth Explorer website, earthexplorer.usgs.gov. You see that there is a search criteria, dataset, selection criteria, and results. One of the first things that we need to do is, if you have a login, log in, and if not, register to log in. In our case, we do have a login, and that makes things faster and easier for us. After we sign in, we notice our username is over here, and there is an item basket empty right here. So we can use our search criteria. If you know the name of the place, we can type it here, or we can also use the map. In this case, we're going to zoom in to the El Paso Ciudad Juárez area and use the map as our set of coordinates. Once we have that set up, we can go to datasets. A number of datasets are available. Or what we want is go to the Landsat archive, go to collection level 1, and we see Landsat 8. Now that we have the geographic area and the sensor that we want, we may need to go for additional criteria. For example, you may decide that you want a certain amount of land cover, let's say less percent of cloud cover. Once we set up the additional criteria, we can click on results. And we find several images, some that are very current. If you know the date in which you took your reference polygons for your ground truthing, you can search for a similar date. In this case, we know that we took our ground truthing in June 14, 2016. So we can define this on the search criteria here, searching for a certain date range. We select the calendar, 2016, let's say from May 1 to June 30th of 2016. And we go to results. And now we only have dates for 2016. Hovering over the different icons for each image shows a little text of what they do, in order that they are like show a footprint, show the browse overlay, compare and browse, show the metadata and browse, download options, add to bulk download, order seen, or exclude from the results. In this case, what we want to do is download it. We click on it and we have different download options. Some of those, like the first 4, are just like a preview of the real data. The real data is the last option, 11.1 GeoTIFF data product, and it's almost 1 gigabyte. We click on download and that may take a little while, a few minutes depending on your connection. Choose a program with which you can open a compressed file, like 7-zip. When the download completes, we can use an uncompressor, like a 7-zip, to uncompress our file. You will see that it's a tar.gc, which is a compressed file inside of a compressed file, a double compressed file. And we can, when we open that, we can see all the different bands from the both sensors. Click the Extract button and download the individual bands 1 through 11. Quality Assessment Image, BQA, and Metadata, TXT, into a local folder. First, let's start QGIS. We'll start QGIS Desktop 2.18. QGIS starts by allowing us to get some tips. Under the Processing Toolbox, we can find the ORFEO Toolbox, or OTB. It is a library for remote sensing image processing. Object-oriented classification, OOC, is included in it. The OTB can be described as a plugin for QGIS to perform image analysis. For the object-oriented classification, we need to have the previously created training polygons that define the land cover classes that we hope to create, which are called also the objective classes. We need to create an image stack composed of the individual bands of Landsat 8 imagery downloaded previously from Earth Explorer. Select in Windows Explorer the first 7 bands of the OLI sensor and just drag them to QGIS. Resize the Layers panel if needed to see which band is which. Once the Landsat layers are added, double-click any of them to access general information for it. Note the spatial reference information. In this case, it's WGS 84 UTM Zone 13 North. Okay. On the QGIS top menu, select Raster, Miscellaneous, and then Build Virtual Raster Catalog. Use the visible raster layers for input. Type your output file and select the spatial reference information. Click OK. Now check mark on Separate and click OK to start the process. It should take just a few seconds. Now, the new image, the virtual raster, is added into our canvas. Select the individual bands and remove them from your Layers panel. Click OK. Double-click on El Paso Landsat 8 image and click on Style. For a natural color approximation, choose for band red, number 4, for the green, number 3, for blue, number 2. You may want to select from the pull-down menu, stretch to min, max, and click OK. We can click on Load min-max values and select a cumulative count cut from 2 to 98%. Load those values and click OK. For ground truth polygon creation, once we have our El Paso Landsat 8 7 bands image stack in QGIS, we need to add our ground truth collected with GPS as points. To do that, we add a new vector layer. We quickly look for it, and here we have it. El Paso training GPS points. We click Open, and we can see in the attribute table that we have IDs and classes for all the points. So we can select a number of points for the developed class covering cities and urban environments. Or we can now take a look at barren land with little or no vegetation. In this case, let's zoom into one of those points. This is our point for barren land, and we need to create a polygon for it. So we go to Layer, Create a Layer, and click on New Shapefile Layer. Type will be a polygon. In the field list, there is a field ID only. We need more, for example, the field class ID. That will be a number. And we need to add the field class, which will be text. And that will be 20 characters long. After that, we click OK. And we need to name it El Paso Training Polygons. We click on Save, and that creates the layer, which is empty now. So we need to add polygons to it. To add the polygons, we need to toggle the editing tool, and then we can create a feature here. It is clear that the barren land stops over here, as described in our notes. This might not be part of it, so I'm going to try to get out of it, and right-click to close the feature. Then we need to type the attributes. The class ID for barren land is 5, and we type barren land as the class. Just like that. We click OK. This is our first polygon. We can keep working on that on other barren land polygons that we have as points of different color. We expand and zoom into another one, and similarly we create a new polygon for barren land. ID will be 2, class ID is 5, and class is barren land. Okay, we can keep working on all of this until we are satisfied. We can click on I. This polygon will be its ID equal to, class ID is 5, and the class is barren land. We keep working on that until we have all of El Paso training, and then after that El Paso accuracy assessment will be polygons to have 2 shapefiles, one to help train the classifier and the other used at the end to verify the accuracy of our classification. After we have all our training polygons and our accuracy assessment polygons, we can check to make sure that we have all the names for classes and IDs you need by opening the attribute table. We have a class ID and names for all the classes in the accuracy assessment polygons. And we have the same for El Paso training polygons, with classes and IDs for all of them. That is why it is important to keep all our GPS notes about classes, location, and extents on the field available to help when creating polygons. So we can double check the name of the class that we are trying to map, and this is crucial to get a good classification result. We expand as needed the processing toolbox to see the complete names of the different algorithms under segmentation. Expand image filtering algorithms also, and discover the first step of an object-oriented classification, that is the exact large-scale mean-shift segmentation, step 1, smoothing. This will smooth the image for us. Double-click on it to start the dialog. Fill in the values as described here. Note that under Help, you can find the definitions of each parameter. Two important values to consider are the spatial radius, which is of the neighborhood in pixel units, and the range radius, which is the Euclidean radius expressed in radiometric units, that is data values in the multispectral space. Both are defined here, spatial R and ranger. Define your filter output and your spatial image output. Click OK to run. Notice that both outputs are added to the layers panel. And we need to notice also that El Paso filter is still a multi-band image with 7 bands. Next, we need to convert the filter image to a 1-band object. Close the catalog for image filtering. This next step will produce a labeled image where neighbor pixels will range distance is below the range radius, and optionally the spatial distance below the spatial radius will be grouped together into the same cluster. Go to Processing Toolbox, ORFEO Toolbox, Image Analysis, Segmentation, Exact Large Scale Mean Shift Segmentation, Step 2. Double-click on it. Select the filter image instead of the default image. Double-click on the filter image. You see that under histogram, it is useful to know what our domain of values is. If we click on the histogram, we can see that the values go up to 30,000. This is helpful. We will set the range radius to 1500. We define the output image as El Paso segmented 5.tif. We click Run and the new layer is added to the Layers panel. To display the segmented image properly, we switch from single gray to single band pseudo-color. We try a maximum of 10 colors for now with equal interval. The mode is continuous and 10 classes. Step 3 is optional. It merges small objects which size in pixels is lower than the mean size parameter with the adjacent region that has close Euclidean radiometric distance and acceptable size. We define the minimum region size as 10. Click on the 3 dots and select Save to File to save the output image as a file name meaningful to you. In this example, we use El Paso output3.tif. For a description of the fields, you can click on the Help tab. Click Run. The output El Paso output3.tif is added to the Layers panel. Step 4 transforms the raster image objects to polygon vector objects. Each polygon contains additional fields, mean and variance of each channel from the input image in parameter, the segmentation image label, and number of pixels in the polygon. Name the output GIS vector file El Paso segmented 5.shapefile and leave the size of tiles in pixels to the default values of 500. Click Run. We can change the symbology of El Paso segmented 5 to make the segments more meaningful. Now, in green and transparent, we can see the polygons behind them. We can right-click on the Paso segmented 5 and choose to open the attribute table. Notice that now we have vector objects that have mean and variance statistics. That is for each of the 7 bands in the input image. For the next step, we will use training polygons vector data called El Paso Training Poly, created as sample polygons from point GPS information, approximate extents, and photographs captured on the field. We will join the training polygon class attributes with the image segments generated in the previous step. In the main menu of QGIS, go to Vector, Data Management Tools, Join Attributes by Location. The target vector file is the output of the previous step, El Paso segmented 5.shape. Set the join vector layer as El Paso training poly.shape. The join layer can be defined as El Paso stjoin.shape. Click Run. This new shapefile combines the mean and variance attributes with information about the classes captured on the field. We can see the ID and the class for each one, and all of them have mean and variance. Open the ORFEO Toolbox graphical interface by searching for the OSGeo4W shell. Click on it and you'll find it. It is on Start All Programs, OSGeo4W, OSGeo4W shell. Navigate to the directory where you have the freshly joined shapefile, El Paso stjoin.shape. On the command shell, type OTB GUI underscore compute OGR layers features statistics to open a new graphic user interface, GUI. The name of the input shapefile is El Paso stjoin.shape. The XML file containing mean and variance of each feature is El Paso stjoin.xml. Select from the list of features mean for the bands 0 through 6. And click Execute. Notice that a new XML file, El Paso stjoin.xml, was created with contents defining the mean and standard deviation of each considered in the previous step. Repeat the last command by changing the name of the input file to El Paso segmented5.shape. And the XML file shall be El Paso segmented5.xml to calculate XML statistics using the same parameters as before. When the green text ready to run reappears, click Execute and then click Quit. On the command shell, type OTB GUI underscore train OGR layers classifier. A new GUI opens. A brief description of this classifier is under the Documentation tab. It trains an SVM classifier based on labeled geometries and a list of features to consider. SVM stands for Support Vector Machine. For the input shapefile, we will use El Paso stjoin.shape. The XML file is El Paso stjoin.xml. The list of features that we will use is mean B0 through mean B6. The output model file name is El Paso stjoin model.svm. On the field containing the class ID for supervision, type the field with the numeric value ID. Click Execute. After finish, click Quit. There is a new model in your directory called El Paso stjoin model svm. On the command shell, type OTB GUI OGR classifier. A new GUI opens. This application will apply a trained machine learning model on the selected features to get a classification of each polygon contained in a layer. The list of features must match the list used for training. The predicted land cover class is written for each geometry into a user-defined attribute field, which we have named predicted. Click Execute and then Quit. El Paso segmented 5, if we open the attribute table, has a new field called predicted, populated with IDs for each class. Now we can symbolize based on this new field for our classes. Instead of a single symbol, can be categorized the column is predicted and we click Classify and we see our 6 informational classes plus a 7th symbol for other unclassified polygons. We click OK. To see the image behind it, we can modify the transparency of El Paso Cemented 5.shape. Now we can see both the image and the segments already classified on top of it. But do you wonder how good is our classification in this tutorial? To use our accuracy assessment tools in QGIS, our accuracy assessment polygons using the ID field and the resulting polygons from the classification, El Paso Segmented 5.shape, need to be converted into images, rasterized. First, we add our accuracy polygons. The tool for rasterizing them is on the top menu bar. Raster Conversion, rasterize vector to raster. And eventually we want the same horizontal resolution as we have for our original image. And we click OK. We repeat a similar process for El Paso Segmented 5.shape. Find on the Processing Toolbox, on the grass, yes, 7 commands, on the raster, the R-Kappa tool. That calculates the error matrix and kappa parameter for accuracy assessment. Input the rasterized classification result and your raster containing the reference classes in the dialog. Give a name to the error matrix and click Run. This calculates the error matrix and kappa parameter for accuracy assessment of the classification result. The assessment report will be written to an output file that is in plain text format and named by the user at the prompt while running the program. This report can be brought into Excel or OpenOffice for formatting if needed. The values in the diagonals mean they do match. The pixels in the classification match the values of the pixels in the accuracy assessment polygons. We can see the percentage of errors of commission and omission and the estimated kappa values. This is just an estimation of how good the classification matches. Below, you can have a category description for each of the classes, so you can relate this to the classes above here, 1 through 6. The kappa statistic or value is a metric that compares an observed accuracy with an expected accuracy. Kappa values of 0 to 0.2 can be considered as slight, 0.2 to 0.4 as fair, 0.4 to 0.6 as moderate, 0.6 to 0.8 as substantial, and 0.8 and above as almost perfect. Values of above 80% accuracy in the classification are preferred. The kappa value calculated overall is 0.35, and the classification accuracy is 66%. Both values are a little under what we would like as minimum. With field-verified data from around the time of the image collection, your kappa values and classification accuracy will be better than the ones shown in this tutorial. I hope you enjoy it and you learn something. Additional help may be provided by contacting Miguel Pavon at pavonma@hotmail.com or 512-466-3936.